Okay, for this video, we'll be going through radioactivity. Okay, so these are the success criteria. Okay, let's start. So for success criteria A, you need to be able to describe the composition of an atom in terms of a positively charged nucleus. You learn it in chemistry that inside the nucleus there's protons and neutrons. And in the outer orbit, you have a lot of negatively charged electrons. Okay, so this is basically chemistry. So all these smaller particles are called subatomic particles. Okay, so it consists of a positively charged nucleus, which is protons and neutrons. Neutrons no charge, protons is +1, and negatively charged electrons, which is -1. Okay, so the strong attractive forces between the positively charged nucleus and negatively charged electrons hold the electrons to the atoms. Okay. So these are the relative charges of the subatomic particles. Electrons is -1, proton is +1, neutron is no charge, neutral. By the way, electron is, the mass is negligible. Okay. And the proton, relative atomic mass is 1, neutron is also 1. Okay, so they have mass. B, use the terms proton, which is the atomic number, Z, nucleon, which is the mass number, A, and isotope. Then success criteria C is use and interpret the term nuclide and use the nuclide notation. Okay, so the proton number Z is the number of protons in an atom. So in a neutral atom, the total positive charge equals to the total negative charge. Now, nuclear number is the total number of neutrons and protons, because just now I told you that proton and neutron have mass. So nuclear number, if we assign a mass of 1 to proton and mass of 1 to neutron, the total number of proton and neutron, I can add up their mass. I will get the nucleon or the mass number. Okay, so the mass of an atom depends on the mass of nucleons in the nucleus of the atom. Okay, so we don't care about the electron for the mass. Now, to find the number of neutrons in an atom, I take the nucleon number, which must be a bigger number, subtract away the proton number, right? Because nucleon number A consists of proton plus neutron. Proton number Z, just the number of proton. So if I take P plus N minus P, I'll get the number of neutron. So nuclides are the various species of atoms whose nuclei contain a particular number of protons and neutrons. So they can be represented in this way. X is the symbol for the element. Okay, so you can get it from the periodic table. And then A is the mass number. Z is the proton number. So the top number will always be bigger than the smaller number. So example, I know sodium is 2311. So this number 11 is actually the number of proton. Okay, so if I know the number of proton and if this sodium is a neutral atom, then the number of electrons will be 11 as well. Okay, so how do I find out the number of neutrons? Number of neutrons is, I take 23 minus 11, I will get 12. So I will have 12 neutrons. Now, what are isotopes? You need to memorize this. Isotopes are atoms of the same element that have the same number of protons but different number of neutrons. So basically, they have the same chemical properties, but just that some are heavier than the rest. Okay, so the most common one is C with a mass number of 12, proton number of 6, right? Then for the same C, some actually have more neutrons. So this one actually have 8 neutrons. Okay, this has 7 neutrons, and the OG one is 6 neutrons. Okay, so these are isotopes. Now, show an understanding that nuclear decay is a random and spontaneous process whereby an unstable nucleus loses energy by emitting radiation. So now we go into the actual part that is concerning physics. Just now is the chemistry as the background. Nuclear decay is a random process, okay, in which an unstable atomic nucleus loses energy How? By emission of electromagnetic radiation or particles, either. So a material containing an unstable nuclei is considered radioactive. So if the nucleus is unstable, it is radioactive because the nuclear forces within the nuclei are not enough to bind the nucleons together. Nucleons are your protons and neutrons. Okay, so what will they do? They will radiate either electromagnetic radiation or particles. Okay, and this radiation or particles emitted can occur anytime and in any direction. That means it's also very random, right? So since the direction of the emission and the time between emissions cannot be predicted, it is not possible to make the radioactive nucleus emit radiation by all this method. Okay, it is also impossible to predict when it will emit radiation. We just know that it will happen, but we don't know when. And we also don't know the direction. Okay, so what does it actually emit? So it actually emits alpha particles, beta particles, and gamma rays. Gamma rays we actually study in the EM spectrum, right? It is actually a ionizing kind of radiation. Okay, what is ionization? You need to know this. We actually learned it in EM spectrum already. It refers to the ability to eject electrons from atoms to form ions. Okay, you learn in chemistry, if the atom loses electrons, then it forms a positive ion, right? So let's take a look at these three emission in detail. The alpha particles is actually the nucleus of a helium atom. The nucleus, that means I don't count in the electrons. So if you look at helium in your periodic table, it should have this nuclide notation 42. So what does this mean? It means that when I radiate alpha particles, a helium nucleus will actually be emitted. So this helium nucleus will actually have 2 protons, and with it has 2 neutrons, right? That's how I make up the number of 4. Because neutrons have mass, protons have mass, each one have a mass of 1. So if I have 2 protons, then I will have mass of 2. And according to the nuclide notation, the mass number is 4, so it has 2 neutrons. Okay, that means this helium nucleus is quite big. It's quite big. So if it's quite big, right, very massive, right? So it has low penetrating ability compared to the other 2. Okay, we are talking about alpha, beta, and gamma, right? So this one, helium nucleus, which is an alpha particle, has the least penetrating ability because it is very big. So if imagine I have a piece of paper, and you know papers actually have tiny pores inside, right? But because the alpha particles are too big, they cannot actually pass through these pores. Okay, so they can actually be blocked or absorbed by a piece of paper, a thin aluminum foil, or human skin, right? So the penetrating power is not a lot, but it actually has the highest ionizing effect. Now, what is ionizing? It refers to the ability to eject electrons, and because it has a charge of 2+, right? Because I have 2 protons, I don't care about the electrons because I'm just talking about the nucleus. And neutron has no charge, right? So it actually has a charge of 2+, and that makes it having the strongest ability to eject electrons from atoms. Okay, so we talk about this, then now we do a comparison with beta. What is beta? Beta is actually a fast moving electron. Okay, so if you can't see from the printout, it actually has 0 and -1. Okay, so that is the charge, right, of the beta. The charge is -1. And does it have mass? 0 mass, because an electron is considered to have negligible mass. Okay, so therefore, if you are talking about the ionizing effect, it is actually lower than alpha, right, because of the charge. alpha has +2, beta has -1. Okay. So how about the penetrating ability? The electron is actually much smaller than protons and neutrons. It's actually much smaller, right? So if it's smaller, then the penetrating power will be better than alpha. Okay, so just now if I have a piece of paper, it will not be able to stop the beta. The beta will pass through. Later on, there will be a diagram that shows it. Okay, so they actually need to be blocked out by a piece of aluminium that is a few mm thick. Just now we just say a thin aluminium foil, that means lesser than that lah. But now if I increase the thickness of the aluminium, then the beta will be blocked or absorbed. Okay. For the last one is actually gamma rays. Okay, gamma rays is actually electromagnetic radiation emitted by a nucleus with excess energy. So basically, this is just pure energy. Okay, so the ionizing effect is the lowest. Why? Because it has no charge. Okay, but the penetrating power is the highest because it's just pure energy. So the gamma can just pass through very easily. Okay, but I can actually block it by using a few centimeters thick of lead, okay, or very thick concrete. So in World War II, actually they dropped the atomic bomb, right? So there's a lot of nuclear radiation. So those people who are hiding in those bunkers are like houses or shelter made up of very thick concrete, right? They can be shielded from the force of the explosion as well as the radiation from the nuclear bomb, okay, from the atomic bomb, right? So those people who are exposed to the radiation, if you learn in our chapter of EM waves, right, their cells will be ionized and then it will undergo mutation. So actually some of those survivors will actually suffer mutation of cells and get cancer. Okay, so this is what we talked about just now. When a nucleus undergoes alpha decay, it emits an alpha particle. So this is similar to this you need to know. What happens if it undergoes beta decay? It will emit a beta particle, which is effectively an electron. Then when they either go through alpha or beta decay, gamma radiation is also emitted. That means there's a lot of energy that's emitted as well, right? So you need to know their penetrating power and as well as their ionizing strength. Okay, so this picture, hopefully it can show you the difference between the penetrating power. Alpha is very big, so actually it is stopped by paper. For the beta, because it's electrons, right, so it can pass through the paper, but it will be stopped by a few mm thick of aluminium. Gamma can only be stopped by a few centimeters of thick lead. Okay, so success criteria F, show an understanding of background radiation. Okay, actually radiation is all around us. Okay, ionizing radiation is the radiation with high energy that can knock off electrons from atoms to form ions. So basically this is not good, right? So we shouldn't be exposed to all this. So who are those that are ionizing? It is actually the UV, right? Too much exposure, it will cause you to have skin cancer. X-ray definitely, right? It will cause the cells to mutate. That means that's why you can't go for X-ray every day. Gamma ray is the most dangerous because it has the highest level of energy. Okay, so all these three are the ionizing radiation. Okay, so there are also other ionizing nuclear radiation. Some are from cosmic ray from outer space, okay, and some are from naturally occurring radioactive materials. So what is background radiation? It refers to radiation, nuclear radiation, in an environment where no radioactive source has been deliberately introduced. That means I don't bring like plutonium or some kind of nuclear radioactive sources. Okay, I'm just in a normal environment like in my living room. There will still be some background radiation. Okay, so it can either be artificial or natural. So natural ones will be rocks, food and drinks, example bananas or carrots, okay, they may also contain radioactive substances, okay, and they account for about 80% of the radiation that we're exposed to, but what we encounter is usually well below the recommended level, so there's no need to be alarmed, okay, unless you travel to somewhere where they just had a nuclear explosion, okay. So this part, using the term half-life, this part is the one that is tested so far I see in a past year paper, okay. So how do we measure ionizing nuclear radiation? It can be measured using a Geiger-Müller counter, so GM counter. There are students who ask me, do I need to spell in full? Yes, I would suggest that you memorize the name of this counter, Geiger-Müller. Then if you are desperate, you forget, you just put a GM counter. And SI unit for the amount of radioactivity is the becquerel, okay? So it's equals to 1 disintegration of the nucleus per second, okay? So it refers to the amount of ionizing radiation released when a radioactive atom, example uranium, spontaneously emits electromagnetic radiation, okay. So the measurement of radiation is sometimes expressed as the rate of counts per unit, also known as the count rate. So this count rate can be measured using a GM counter, okay. So they only talk about EM radiation, right? So it measures the EM radiation. It is because when it undergoes alpha or beta, right, okay, it also emits gamma. So by measuring the amount of gamma radiation, I can know the count rate. So to measure background radiation, I need to remove all known radioactive sources, okay. So start the GM counter and the stopwatch and stop the counter after 10 minutes and record the number of counts and calculate. So repeat measurement at least once to calculate an average value, okay. Yep. So to measure radiation from radioactive sources. So now if let's say I have a sample, let's say of sample of uranium, I want to calculate or to measure the radiation, I need to first account for the background radiation, right? Then I can subtract the background count rate to obtain the corrected one, okay. So this corrected one is actually coming from the radioactive source and not to take into account the background radiation. Okay, so why do I need to do that? Because I need to go and calculate half-life. Most questions will ask you to calculate half-life. As nuclear decay is spontaneous, we will not know exactly when a particular nucleus will decay, okay? But every nuclide has a fixed rate of decay. The scientists have already done all these experiments to know, okay? So predictions about the decay of a large number of nuclei of a particular nuclide can be made because it has a fixed half-life. So example, in this case, we have iodine 131, okay. So initially, it started off with 120 millions, right, of atoms. Then after one half-life, okay, half-life is actually a time taken for half the nuclei to decay, okay. It's actually the time taken. So initially, I started out with 120. 120 divided by 2 is 60. So I measure at 60 and the time taken, and it happens to be 8 days, and therefore the half-life will be 8 days. So how do I confirm that? 60 divided by 2, I get 30. So it decays from 120 to 60, 60 to 30. And if I go and measure the time taken for it, I will see that it actually has the same half-life of 8 days as before. That means the half-life of iodine 131 is 8 days. Okay, so the last one confirm at 30, again divide by 2, I will get 15 millions. That means now if I check the number of atoms left, there should only be 15 million. And true enough, the half-life is still 8 days. Okay, so this is how I get the half-life, 8 days. And half-life is actually the time taken. Okay, so now I can give you another iodine 131. So imagine now I have 240 millions. Okay, how long will it take for it to reach 120 millions? Okay, so half of it, right? I will know that is 8 days. Something like that. Okay, so the number that we start off with may not always be the same, but the half-life, which is the number of days or the amount of time taken for half of the sample, okay, the time taken for the sample to drop to half of the original. Okay, I hope I'm making sense here. Okay, so this is a typical question. I start off with 420. Okay, so after some time, after 250 minutes, I ended up with 20. So actually this 20 is the background count. Background count, right? Because after that, it doesn't change. By right, it should drop to 10, but it doesn't. So I can safely conclude that this 20 is the background count. That means how much of this count rate actually comes from the radioactive sample. It's actually 420 minus 20, which I get 400. So actually, I should say at time 0, 400 is, the count rate of 400 is due to the nuclear sample. So 400 divided by 2 is actually 200. Now I'm trying to find the half-life of this sample. So I should go to 200 plus 20 because I need to take into account the background count. So instead of going to 200, I should go to 220. This is taking into account the background count because it is still happening, a background count of 20, right? So then I get the half-life of 20 minutes. Okay, so how do I get to check? The next time when it decay is after one more half-life, right? So I take 200 divided by 2. Why don't I take 220? Because the 20 is from the background count. The 200 is actually from the nuclear sample. So I should get 100. But instead of going to 100, I should be going to 120. So I need to come to here, 120 roughly, and go down. It should be at 40 minutes. So 0 to 20 is the first half-life, 20 to 40. Okay, so this question is more complicated because there is this background count. I hope you can maybe replay this video again to understand why I take 420 minus 20. Where does this 20 come from? And then after that, even though I get the count rate from the nuclear sample, I divide by 2 to get half of the nuclear sample, right? I still add on 20. This is important. They like to test this. Okay. Okay, this part I will not really go through in detail. This is the application and the hazards. You have to read it by yourself. How will the questions be asked? They will ask you, why do I use alpha? Why do I use beta? And why do I use gamma? Okay, and sometimes they may say this alpha has long half-life. What does long half-life means? That means if it has a half-life of 40 years, example, that means I have, let's say I have 20, the count rate is 20. After 40 years, it will become 10, okay? After another 40 years, another half-life, it becomes 5, right? So you find that if this sample is introduced into my body, I will still be receiving radiation after 80 years, you know. So do you want your body to be subjected to this kind of radiation in your body? I don't think so, right? So that is also a possible consideration when they choose the kind of radiation. Okay, so firstly, they must make sure that it is their choice. Okay, under the application is whether is it highly ionizing. Okay, do I need it to be highly ionizing? If I don't need, then I'll choose the not so ionizing kind of radiation. Okay, next thing I need to consider is the half-life. Let's say I use a certain radiation for cancer treatment. So let's say after a few years of applying this radiation to my cancer treatment, right? Do I want it to continue to ionize my cells even after my cancer is cured? So maybe not, right? So I'll choose something that has a lower half-life. You know what I'm saying? Yeah, so these are the applications. You have to read it by yourself. Okay, then after that is the hazards, right? So while radioactive isotopes are used in the diagnosis and treatment of cancer, they can also damage healthy cells, right? Too much of a good thing is not so good. Too much of something is not good lah. So the energy carried by the radiation can actually kill cells and cause mutation and cancer. These are the effects of having too much radiation. Okay, so they can cause cancer, they can stunt children's growth. Okay, they also affect plants and animals. They could suffer from mutations, stunted growth, or reproductive effects. Please don't write things like they become zombie. Okay, so how do we protect ourselves from radioactive materials? Well, we limit the contamination. Okay, so common sense if something happened, you leave the immediate area quickly. So the most recent thing that happened was the Fukushima. Their nuclear plants had a meltdown, right? So everybody evacuated, not just because of the tsunami, but also because there is a lot of radioactive activities there. Okay, so they are supposed to leave the area quickly and remove the outer layer of clothing, okay, as the material may be absorbed on the clothing. Okay, then wash all exposed part lah. So, and also to reduce the exposure. Okay, so after the Fukushima incident, right, the Japanese government was actually looking for volunteers to go in and check the amount of radioactivity. Okay, so they actually have to ask volunteers. So normal people, they will try to reduce the exposure, try not to go in. But if they had to go in, they have to be shielded up. Okay, so they have to wear protective clothings. Okay, yep, and I think that's about it. So I think you need to know how to calculate half-life. Okay, so if you look at your tutorial, most likely they'll ask you to calculate half-life. They'll ask you to do your nuclide notation. Okay, that's a simple one, calculating number of neutrons and all that. They'll ask you to know about, to talk about what is alpha, what is beta, and what is gamma. They'll ask you about factual recall, what's the ionizing and penetrating power. Okay, then of course they will ask you for the what you call that, applications, hazards, okay, and how to what is called that, protection. So you need to know some facts about all this. Okay, so application, hazards, and protection. Okay, so maybe you can try doing a tutorial, then I will upload the answers, then you all can see how well you are doing this chapter.